Look at the scale of modern Asian infrastructure. High-speed rail networks, massive port expansions, and entire smart cities are being built at staggering speeds. Managing the physical logistics of these multi-billion-dollar environments is intensely complex. To handle that complexity, developers rely on digital nerve centers. Building Information Modeling, or BIM, and the Common Data Environment, CDE, are deployed to synchronize design, engineering, and construction into one cohesive digital ecosystem. These platforms operate under strict international frameworks. Major projects mandate compliance with protocols like ISO 19650 to guarantee that information flows cleanly across different disciplines and software tools. Yet, an analysis of megaprojects across Asia reveals a persistent failure. Despite the technical standards, digital coordination frequently collapses upon implementation. Data packets meant to inform downstream engineering fragment into isolated, unusable clusters. The presence of a technical standard does not guarantee compliance. An advanced protocol cannot prevent data fragmentation if the workforce operating it lacks a structured framework to govern that information. There is a pervasive assumption in the construction sector that digital integration is solved through procurement. Firms purchase the latest BIM software, hire proficient 3D modelers, and expect seamless collaboration. But building information modeling is a socio-technical system. The technological tools are only effective when they evolve in lockstep with organizational processes and strict information management. Research shows that treating data governance and human capital development as separate domains is exactly what derails these builds. The rules governing the data must be tied directly to the training of the people creating it. When developers ignore workforce competency, a multi-million-dollar digital governance system quickly degrades into a highly expensive static file repository. Architectural design is the foundational entry point for project data. If models are created without strict ISO 19650 compliance, data leaves the source unstructured. These bad inputs bypass governance standards, striking engineering and construction phases, triggering severe warnings and massive rework. Structural and mechanical engineers are forced to manually reinterpret the models. They spend critical project hours rebuilding the foundational data just to make the files usable for their own calculations. These early-stage errors permanently degrade the final product. By the time the facility is handed over to the management team, the as-built information is too inconsistent to be reused for operational maintenance. Correcting this requires a shift in how the discipline is viewed. Architects must be trained as strict custodians of information quality rather than just aesthetic designers. The integrity of early-stage data creation directly dictates the entire lifecycle performance of the physical asset. We can see this dynamic play out across three very different institutional environments managing megaprojects today: Singapore, China, and Thailand. Singapore operates with high regulatory maturity, embedding BIM mandates directly into government approval processes. However, smaller subcontractors often lack access to continuous professional development, exposing critical training gaps that slow integration. In China, massive state-led mandates drive implementation through large enterprises. Yet because the skills gap between urban firms and regional contractors is so wide, data workflows frequently fracture at the interfaces between the design and construction phases. Thailand represents a market driven by pilot-based adoption. Without binding national mandates, common data environments are often reduced to passive, unstructured file-sharing folders, resulting in highly inconsistent data quality. While the regulatory frameworks in these three nations vary wildly, they share the exact same point of friction: human capital readiness. Whether a project relies on strict government mandates or informal agreements, an unmanaged, undertrained workforce will always compromise the integrity of the data. Fixing this systemic failure requires a specific four-stage structural solution: the BIM Talent Pipeline Framework. The first stage is education and training. Higher education institutions and professional programs must completely abandon software-only instruction. The curriculum must emphasize interdisciplinary collaboration and life cycle information management. Then, the second stage, certification and standards, bridges academic theory and project application. Here, practitioners formalize competencies against strict international mandates. This step serves as the ultimate quality assurance mechanism. It proves that a specific architect or engineer understands exactly how to structure their deliverables to meet the project's macro data governance rules. Without this formal certification step, developers have no quantifiable way to ensure an individual's output will actually sync with the master digital environment. Stage 3 is industry practice. This is where those certified competencies are finally deployed into a live project environment, interacting directly with a synchronized common data environment. To maintain this structure, organizations must institutionalize specific, dedicated data roles, like information managers, whose sole job is to actively govern the CDE and reject non-compliant data. The final stage is continuous development. A digital network is never static, which establishes the absolute requirement for lifelong learning and professional adaptation. As the construction sector integrates data-heavy technologies like digital twins and AI analytics, the baseline for competency is constantly shifting upward. This entire pipeline operates as a cyclical process. The friction and successes observed in the live industry environment must feed directly back into academic institutions to update the educational curricula. Without continuous industry feedback and adaptive skill renewal, the human capital stagnates, and even the most tightly governed digital systems rapidly become obsolete. But the BIM Talent Pipeline cannot survive in a vacuum. It requires a macroeconomic support structure to keep it moving. The support structure is known as the Education Industry Government, or EIG, partnership model. The government provides the necessary policy instruments, legal mandates, and crucial training subsidies. This financial support guarantees that smaller enterprises aren't priced out of the digital transition. Industry and education then align their objectives, ensuring that the theoretical skills taught in the classroom match the real-world operational demands of the construction market. A sustainable digital transformation across an entire economy only occurs when policy, practice, and education are inextricably linked. Consider the physical reality of a successfully operating smart city infrastructure asset, one continuously managed and maintained by its digital counterpart. The ultimate goal of adopting these complex modeling platforms goes beyond environmental efficiency. It is about achieving deep organizational resilience that lasts for decades. To get there, firms must make a mandatory operational shift. They must abandon the strategy of mere software acquisition and start defining strict information responsibilities for every member of the team. Data management and human capital are not separate problems to be solved in isolation. They are a single, interdependent ecosystem. The longevity and performance of a multi-billion-dollar megaproject do not depend on the software purchased. They depend entirely on the continuous renewal of the human minds managing the data.